Hello everyone, my name is Hiroki Nakagawa. I work with Okayama University and Osaka University, Japan. I am the second author of this paper, but since the first author has already been graduated from our university, I present our today. But deeply apologize that I cannot attend the conference today because of the duty in my university. This work is on an implementation framework for all self-adaptive systems. Self-adaptive systems can autonomously modify their behavior to adapt to changes in their environment. One common approach is architecture-based adaptation, where a system is represented as a set of components, each with a single responsibility. In this approach, adaptation is conducted by replacing components. A component usually replaces with another capable of performing the same responsibility. Compared to code-based adaptation, architecture-based adaptation enables reasoning at a higher level of abstraction. This work also addresses time constraints. In many real-world systems, tasks must be completed within certain time constraints. Violating these constraints causes serious issues. Therefore, we need an adaptation mechanism that not only provides component-based adaptation, but also verifies time constraints. We consider such architecture-based self-adaptive systems. But when combining the two conventional adaptation approaches, a problem arises. Here we have a simple flow diagram of a robot. Where the rotate action takes 20 seconds and the move action takes 30 seconds. Now suppose this flow violates a time constraint. To satisfy the constraints, the processing method in the flow diagram are adjusted. We will verify the required time and identify a method to resolve the violation. In this case, we can reduce the execution time by replacing the method called normal rotate with a faster alternative, high-speed rotate, which only takes 10 seconds. This seems to solve the problem. So the component configuration is updated in response to changes in the flow diagram. If the component to be modified is also involved in the other task's execution, the processing method of those tasks must also be updated accordingly. In this case, modifying the processing method of high-speed rotate results in the updated component being used in other tasks as well. Consequently, the processing method for the task move is changed to high-speed mode. As a result, a discrepancy arises between the processing method defined in the flow diagram and those in the component configuration. So we need to solve this problem. To explain an approach that solves the problem, I will redefine the relevant concept at the beginning. First of all, a task is a logical function defined in the flow diagram. The task is completed by various processing methods, which uses components. So, a processing method corresponds to a set of components used to perform a task. Tasks therefore correspond to one or more components. Importantly, multiple processing methods are defined for each task. These methods differ in the component composition. The system can dynamically switch them to adapt to time constraints or failures. For example, a navigation task may use either component 1 and component 2, or switch to component 3 if the first method becomes insufficient or infeasible. This switching is done by reconfiguring the system's architecture at runtime. To sum up, we define a mapping relationship between tasks in the flow diagram and components in the configuration. In our framework, we define a task as a unit of logical functionality represented in the flow diagram. Each task is realized by one or more components. These components are grouped together to define different processing methods for the same task. For example, the task A uses components 1 and 2, while task B can be implemented using method alpha or method beta. Method alpha uses component 4 and method beta uses component 5. This mapping enables flexibility. When one method fails to meet time constraints, the system can reconfigure itself by replacing components and switching to an alternative method. This design is fundamental to enabling runtime adaptation with verifiable time constraints. Okay, let me now explain some formulae, which lay is the foundation for linking tasks to architectural components. The first formula defines an equivalence relationship. By using this, we define equivalence classes. This formula maps tasks to system components. Finally, this formula is used for find components that can solve a task. Here, the function function solve maps a task into a power set of types. And this formula finds all components to be required for solving a task. These three formulae allow us to rigorously model the connection between abstract tasks and concrete implementation components in a verifiable way. In our framework, we use a component type as a label representing the responsibility of a component. For each component type, only one component is connected at a time. During adaptation, the connected component can be replaced by another unused component of the same type. This means that the component type serves as a key to identify alternative components when adaptation is required. In addition, each task is associated with the component types needed to realize it. With this linkage, when we need to change the processing method of a task, we can determine exactly which components must be reconfigured in the architecture. By using this linkage, we implement a time constraint verifiable framework. This framework allows us to predict the task processing time during component replacement. The framework consists of two key elements. The first one is the component-oriented programming framework. In this framework, each component is assigned a type representing its functional role. Tasks are then linked to the required component types, not specific components. The second one is the time constraint verifier. The verifier enables the prediction of execution time by calculating the performance difference between components and the contribution to the overall task time. By using the framework, we can not only identify which components to replace, but also estimate the effect of replacement on task timing in advance. To evaluate the effect of changing a processing method, that is to predict the processing time, we introduce two metrics. The first one is the performance difference index, PDI. This metric tells us how much faster or slower a task becomes after switching its processing method. A higher PDI value indicates better performance. The second one is the contribution rate, CR. This measures how much a task contributes to the total execution time. The higher the CR, the more critical the task is in terms of performance. These two indicators help us to determine whether changing a task's method will effectively address a time constraint violation. By focusing on high ECR tasks with high EPDI, we can maximize the benefit of adaptation. This approach enables rational decision making in architecture-based self-adaptation. This is the adaptation process using a framework. The adaptation process begins with monitoring the processing times of tasks during execution. Then the verifier checks whether the measured processing times satisfy the predefined time constraints or not. If a violation is detected, our framework estimates a candidate adaptation by proposing the replacement of disconnected components with alternatives from the same component type. We use PDI and CR values to predict how much a replacement will affect the task's processing time. Once a configuration is proposed, the framework re-verifies it. If the proposed configuration resolves the violation, the new configuration is applied, thus completing the adaptation cycle. Okay, to evaluate our framework, we implemented a prototype robot transport system as a self-adaptive system using LEGO Milestone EV3. The system's main function is to transport objects, that is, to collect, move, and unload them. Time constraints are imposed on both the time until collection and the time until unloading. We observed the behavior when arrival at the base is delayed due to obstacle avoidance. This is the initial component configuration. If the robot is delayed, the adaptation engine detects the violation of the time constraints. Then the framework finds a high-performance component and replaces the component for the go-back task from back to base to a longer but unblocked path called back to base 2. After predicting and verifying the new processing time, the system updates its configuration. This is a highlight video of the experimental results. When the robot was returning to the base, an obstacle was present, which causes the return time to be delayed to 57 seconds. At this point, the robot detects a violation and searches for an adaptive behavior. As a result, it finds an alternative component back to base 2, which is faster and switches its behavior. We can see that the return time is slightly improved. As a result, the return time was reduced to 31 seconds. This is a log of the experimental results. First, the robot detects an obstacle while returning to the base. To avoid it, the arrival is delayed to 57 seconds. And as a result of verification, a constraint violation is detected. At this point, the system estimates the processing time if the component back to base is replaced with back to base 2. And the estimated time is 28 seconds. Since it determines that the violation will be resolved, the component is actually replaced. In the previous video, the actual execution took 31 seconds compared to the estimated 28 seconds. This shows the execution time for each task. In the experiment, an obstacle was placed at the 30th cycle. And at that timing, a constraint violation was detected. Okay. And so from the 31st cycle onward, due to the component switch, we can observe that the execution time of the go back task has been reduced. In this study, we also focused on the scalability of our framework in terms of search time. We compared the time required to find a suitable configuration for a task. We measured how fast our framework can search for alternative processing methods once a violation is detected. We considered two approaches. The first one, named S1, is our proposed method, which uses component types and predicts processing time based on performance differences. The second one, named S2, is a baseline approach where both the flow diagram and component diagram are separately revised. In this experiment, we increased the number of tasks associated with a component and measured how long it takes to search for a valid configuration. This figure shows the experimental result. As shown in this figure, with the baseline approach S2, the more tasks that involve the change component, the more time is needed for modification and consistency checks. On the other hand, with our approach method S1, the search time remains nearly constant, regardless of the number of affected tasks. This shows that our method scales better and is more efficient where multiple tasks should be modified for adaptation. Okay, to summarize, we proposed an implementation framework for all self-adaptive systems that can verify time constraints. Our framework uses component types to classify components and link them to tasks. We introduced a time prediction mechanism based on PDI and CR. This allows the system to select appropriate component replacements and verify their effects on processing time in advance. The result of two experiments demonstrated that our framework enables time-aware adaptation with scalable search time and successful behavior modification. As for future work, we plan to automate PDI and CR setting. We also plan to apply our framework to various types of self-adaptive systems and use cases. We believe that this approach can contribute to practical time constraint self-adaptation in the real world. Thank you for your attention.